So if I could have your attention, please. Thank you. So welcome to the, it's on. Okay. So welcome to the CSAC research seminar that we have this time every Tuesday. I'm Rod Ewing. I'm one of the co-directors at CSAC. And today it's my pleasure to introduce Lindsay Rand. Lindsay just completed her PhD this year at the University of Maryland's School of Public Policy. The title of her dissertation is Schrodinger's Technology is Here and Not, appropriately, a socio-technical evaluation of quantum sensing implications for nuclear deterrence. Prior to joining us at CSAC, she was a Stanton pre-doctoral fellow in the nuclear policy program at the Carnegie Endowment for International Peace. And then prior to that, she's been a research associate at RAND, an NSF fellow, and an intern at the Naval Research Laboratory. So we're really looking forward to her presentation. And Lindsay, it's all yours.
Okay. Yeah, so thank you everyone for coming to my talk. I'm going to be presenting a small window in which I look to consider the broader question of when and how new technologies could impact nuclear deterrence. Specifically, I look at how high accuracy sensing could impact second strike capabilities, which hopefully you'll have a better idea of what all those concepts mean by the end of the presentation. And then I'll just kind of show where this research is pushing me, which is the reinventing vulnerability part, and kind of understanding how this newer wave of high accuracy sensors actually fits into a longer history of cyclical reinvention of vulnerability concepts as other previously emerging technologies actually impacted them in the past. So the issue of new technologies in nuclear deterrence is something, I'm actually quite certain a lot of people have already presented in this room. It's generated a lot of concern, and the concern can range from disruption to strategic stability, disruption to the balance of deterrence, potentially ways in which it could bolster strategic stability or deterrence, all sorts of things. Sometimes you see headlines like, could a new technology allow for better tracking of stealth capabilities, which may imply offensive capability improvements? I actually really don't believe this one. This came out in August, and I can go into greater detail later at the end, but this one's kind of funny. They were like proposing tracking subs with tiny bubbles, but it's not a component of this research. It's really not technologically feasible at all. But sometimes you see concern over improving defensive capabilities as well. So could new technologies actually allow for better defense of second strike capabilities? And sometimes it's not really in response to any specific impact on a capability so much as impacting a balance of power or technological power between two countries. These are just examples, and actually, those are catchy headlines, but this is actually occurring in academic media or in academic scholarship as well. So you have scholars talking about how the second strike is going to be vulnerable, and they come up with a range of policy implications that really do vary, but at the end of the day, these assertions generate a lot of concern over the longevity of deterrence. And actually, I think is interesting in new technologies and is kind of uncomfortable for me coming from the technical side is, honestly, it really doesn't always matter whether or not these claims are based in technological truth. The perceptions that policymakers have about new technologies ultimately do engage or impact their willingness to engage in arms control and how they decide to construct their nuclear force architecture. And so, that was one of the driving reasons why I wanted to look at this and try to figure out the balance of what's going on with these claims, where they're coming from, whether they're rooted in technical, facts at all, or whether they're driven by strategic or social pressures. So like I said, today I'm going to focus on a very narrow chunk of that issue, which is the second strike capabilities for nuclear deterrence, which largely revolve around deeply buried ICBM silos and mobile nuclear infrastructure like submarines or road mobile missiles. And this growing concern that new sensors are going to allow for constant surveillance of these of the submarines, particularly, or road mobile missiles, or for higher accuracy to target silos, which would significantly impact the second strike. But like I said, these are coming at the same time. These assertions are coming at the same time as people who have long been in the field, both on the capability side, so non-technical people who just have a lot of experience in deterrence, and people on the technical side say that this is unlikely. So what I'm also trying to figure out what's going on with this as well. And so the motivation for this is the second strike underpins deterrence. So the ability to secure a second strike or have an assured retaliation capability, there's a lot of terms for it, just ensures that you can operate deterrence by punishment or threat of retaliation in case an adversary were to launch a nuclear weapon at you. And so the way that you assure a second strike to try and stabilize deterrence is to hide a bunch of delivery vehicles, to secure them from attack by putting them deeply underground or under reinforced concrete or steel, or just increasing the volume of nuclear delivery vehicles. So that's how you operate that in practice. And then in strategy, whether you perceive that your second strike capabilities are secure or that of your adversary or ally, then it informs how you both engage in crisis stability or in crisis scenarios. So it might impact your willingness to escalate either intentionally or unintentionally. Or what I focus on is arms racing stability as well, because I think a lot of times people want to focus on how new technologies impact crisis scenarios. But as someone from the technical community, I'm also interested in how it informs our decisions for pursuing certain technologies or for building up our nuclear forces. So how do high accuracy sensors fit into the picture? So if you think about the methods that I talked about for how to secure a second strike, you secure them from attack through burying them or through hiding your targets. And sensors could impact that by improving precision strike capabilities, which could allow you to target the deeply buried silos and potentially have a higher success rate of taking them out. And it can also improve your tracking and detection capabilities and your ability to constantly be aware of where the mobile targets are. Why this is so important is because if policymakers believe that sensor-enabled capabilities like those could significantly undermine the second strike in these two areas, then the only policy response or the best policy response would be to increase arsenal size or complexity. And that's why a lot of articles that talk about the vulnerability of the second strike argue that we should not be engaging in arms control on new technologies or force structures. And we should be willing to increase our arsenal size to respond to the second strike vulnerability. So that's why I think this is a very important issue. I look at quantum sensors, which I feel like often evokes this sort of like strange image in people's brains. I don't really know what this is, and I'm not going to explain this figure. What I will do is try to, I know this one's kind of trippy, is just kind of give the basic premise and promise for the technology, but I'm happy to talk if there's like any quantum nerds after the presentation. So the premise is that quantum sensors are the frontier of sensing technologies, which is why I focus on them, because if I really want to counter these claims about the vulnerability of the second strike, I want to look as far out as possible. And so quantum sensors leverage or promise to leverage, they don't actually leverage this yet, but they promise to leverage entanglement and superposition to measure physical properties with higher sensitivity or in more challenging environments. The promise of this is that extremely high sensitivity can allow you to have really good measurements of electric and magnetic fields, gravitational fields, acceleration and time. This can improve your navigation capabilities or your ability to detect small perturbations in these fields. It's useful for detecting things like submarines. Well, the caveat is, like any emerging technology, I mean, there's a lot of technical challenges that still have not been addressed. With anything that improves sensitivity, you also come with a lot of noise, signal to noise issues. And these have not really been tested in real world environments outside of the lab, despite the fact that there's been all these assertions about them. And actually, a lot of the promise that people are suggesting that they will bring are related to the ability to entangle multiple sensors or network them. And if you've ever had to do any sort of entanglement in any lab, it's very, very hard in a lab setting, let alone in a real world environment. So I think, that's kind of a lot of the caveats, although I'll get into the other ones later. So this helped me narrow down the broader research question that I kind of discussed, which is when and how could new technologies actually disrupt or impact nuclear deterrence? And why is this issue coming up so much? But what I do is I take in this much narrower approach, which is looking at, could something like a really far out frontier capability like quantum sensing undermine something that really underpins deterrence, like the secure second strike capabilities? So there's a lot of literature on emerging technologies. Like I said, there have been a lot of articles, there's been a lot of policy briefs, there's been a lot of op-eds. They cover all different aspects of emerging technologies. Generally, I think there are four major issues. One is there's often an omission of historical cases, which I think is because people just get in the mindset that these are new capabilities and we don't have historical precedents. But actually, if you look at historical cases, a lot of the technologies that we're talking about when we're saying emerging technologies are actually pretty old. So they themselves are the historical precedent. But then there's also similar characteristics to historical technology developments that we can use to understand how policymakers have made decisions about these in the past. Just a lack of technical analysis or any small technical consideration really constrains the ability to minimize the amount of uncertainty as much as possible, and to kind of point out key barriers that we could expect that might push back on some of the hype. And there is this, in a lot of the articles, some sort of a positivistic assumption that we can measure strategic effect that actually doesn't account for the fact that there's a lot of disagreement on what this ideal strategic layout is for deterrence. And so it doesn't really recognize these underlying disagreements. And I think that's because a lot of people hope that they can bring in new technologies into the discussion to try to revitalize long-held disagreements. And then the final one is, a lot of them just kind of ignore non-strategic and non-technical influences altogether. And what I mean there is social. So social and parochial interest among technologist communities or strategic communities that aren't really rooted in technical feasibility at all or strategic considerations, but are rooted in organizational theory or social theory. And so I propose improving this with a more interdisciplinary approach where I bring in technical literature to try and constrain some of the uncertainty. But I also draw upon this growing field called science and technology studies to try to understand some of the social phenomena that is driving some of the hype in this field. Okay, so I first proposed an analytical framework that's quite similar to Christopher Chiba's. I don't know if anybody's read Chiba's New Technologies and Strategic Stability, where he looks at how you can map technologies and their strategic effects. So what I do is I separate technology characteristics to give you an area for where you can look at what is actually changing when people are talking about newer emerging technologies. And then I look at how this impacts capabilities and strategic stability. And importantly, I separate technology and capabilities because I think people often conflate the two and they assume if you get this technology, then you will have this capability. And that's almost never been the case. So normally it's a longer road to transition once you get some sort of new sensor to actually deploying it and then getting some strategically relevant capability that you could theoretically expect, but that takes a lot longer to come to fruition or might never come to fruition. But then, like I said, because I'm also interested in not centering the analysis around the technologies, but the people that produce them and that acquire the technology or pay for the technology acquisition. I also look at both the technologists who are involved in developing the technology and then the capability seekers is what I call like the policy community that seeks out new technologies to satisfy capability interests. And then I also look at a third group, which is like I don't know, I don't have a good term for it yet, but this group who has the technical knowledge and the capability awareness to inform whether or not there is hype. So I'm interested in that third group because I think that can provide some positive feedback or useful feedback to push back against some of the claims. So the way that I look at my research is breaking out into historical case studies to kind of support my framework that I propose. And then I apply that to a current case study, like I said, quantum sensing, and do a technical analysis, and then show how even if you do a technical analysis, you still have remaining uncertainty that is then leads to bifurcated policy and strategic stability assessments. And then I also look at some of the social and parochial factors that are influencing quantum sensing as well. Okay. So for the historical case studies, the key goal that I had was to assess the interplay between the technical, social, and strategic factors. So I started out just thinking I wanted to look at technical feasibility and strategic motivation to see if the acquisition of these technologies is more motivated by improvements in the technologies or some sort of strategic rationale, which then ultimately led to me adding the social factor, because as I'll show, sometimes you could have interest in a technology or capability that's not driven at all by technical feasibility or strategic motivation primarily. And so I really wanted to look at how these play out over time, but additionally how they change over time as technologies evolve and as geopolitics change, and you have the changes in the strategic motivation for the technology. So I will just give a brief overview, but when I started, I thought I was gonna just like divide this and be like, okay, when was something technologically feasible, and was there a clear strategic interest? So I started with satellite imagery and specifically the Corona program very early on, where it was deemed technologically feasible, and you were able to achieve it in 6 years, and there was a clear strategic interest. I took on parts of missile defense, which was kind of crazy because it's way too long. And actually, when you look at missile defense, initially there was no technological feasibility, but clear strategic interest. Although there were completely different perceptions. And that's why, these are kind of arbitrary grids, and I'm sure we can all debate them at the end. And so, this whole idea of mapping this out was kind of like, a little bit of a fool's errand, but it at least gives you some way to conceptualize whether or not policymakers are making decisions based on what they perceive as technological feasibility or strategic interest. But obviously, missile defense has moved basically between all 4 grids at any point in time. Then I looked at hypersonics, which has an equally long history. And, actually early on, they really thought it was going to be very technologically feasible to produce a hypersonic plane, even though there weren't clear strategic interests at all. And then that one has now moved, back to not technologically feasible for decades. And then it moved back to technologically feasible. And really throughout all of that has not had a clear strategic interest in the US specifically. And so it's kind of interesting to see what the driving motivation is for that. And then I looked at isomer weapons or hafnium weapons, which is the use of something that people have never actually figured out if it's real. Most physicists believe it's not real, that you can't actually trigger isomers. But it has been funded for decades. And there's also no clear strategy for how you would even use an isomer weapon, because there's no way to, like, the best case scenario use would be that you'd throw it as a grenade, but then, you would also, if it actually worked, have isomers come at you or isomer fission. So, there's just a lot of issues with that one. And then finally, what I wanted to do was, because the ballistic missile defense moved around so much, try to find like a null case where there was something with clear strategic interest and no technological feasibility. And actually that is where the psychics fit in. So I looked at the funding for 25 years of psychics, which has no technological basis at all, and actually is one of the downfalls of the program, surprisingly. But it was funded for 25 years because there was such a high strategic interest to be able to know where things were at any given point in time, even if you had no technological basis to prove that it worked. So that one actually worked really well for capturing that corner. So I'm not going to go into each case study, but can in the Q&A or after it, if anyone's interested in psychics. But But I think, this important thing that this showed is that technological feasibility and strategic value are obviously time variable and ambiguous. So you can't really break out whether policymakers are making decisions based on rational information. And also this just changes over time. And so what's important to understand is how the actor networks of the technologists and the capability seekers change over time and respond to changing interest from policymakers. So that is why I think focusing on the actor network is extremely important in the case of new technologies, because once that connection between the technology community and the capability seeking community is formed, becomes a really robust network that is hard to push back upon and try to push for technological restraint. So technologists can engage with the civilian sector to try and wade out cycles of political disinterest. And on the policy side, in the case of psychics and other things that seem very not technologically feasible, you can make a case for them on the basis of hedging against surprise. So there are just ways to maintain a robust network. Interestingly, you can fund a technology through any number of ways, even if it's not technologically feasible or of strategic value, I guess. And so I think the key thing from this is trying to identify if technological restraint is possible. And from my analysis, it's very rare, but sometimes you have periods with technical oversight and recognition, not just of not having strategic value, but of a clear strategic risk for developing a technology. And then also an alignment of both social pressure. So I have economic constraints, but also you can have social pushback on the normative side of a technology. And so sometimes those do align and you can push back against like the isomers or the psychics, in some cases, blissful events. So then moving into my quantum sensing case study, like I said, I wanted to look at quantum sensing and try to figure out if it would impact the second strike capabilities. And so I looked at 2 use cases where quantum sensing is most likely to impact second strike capabilities. And here's where I brought in the technical literature and tried to understand what sort of obstacles we're likely to see when we actually deploy quantum sensing, or if we were to deploy quantum sensing in real world environments. What the technical literature actually shows us compared to promises that have been made in strategic literature. And actually one of the hardest parts of doing the technical analysis was the lack of publicly available information on capability requirements. So trying to understand, magnetic signatures from subs obviously is not published. So you have to come up with your own estimates and understanding sources of inaccuracy in missile navigation. So a lot of it is kind of, just estimations based on parameters that you know. So for example, in the case of submarine detection, I actually got to keep the equations in the slide because I know there are technical people at CSAC. So normally if I do this for policy people, I will take out the equations. But for the sub detection, actually is kind of an interesting equation because there's really no quantum at all. It's just a magnetic field propagation equation, which I plugged in the parameters for a Columbia class submarine. That's the new class for US nuclear submarines. And then with the background magnetic field, figured out how the anomaly would propagate, and then solved the lowest value for disagreement, where I plugged in the sensor sensitivity into that and then solved for the distance. And that gave me the detection range based on the sensitivity of the sub. So it's just kind of an estimate, but it gave me at least a scale for how far you could reasonably detect a submarine. And so there's 2 interesting pieces to pull from that equation on the right. One is if you look in the top left-hand corner, you see surfs and squids are the magnetometers with the highest sensitivity. So in the case of sensitivity, you actually want a low value. That means it's a better sensor. It's able to detect a smaller degree of difference. And so those have the longest detection range for that reason. And the interesting thing is those are not new at all. So those are really old sensors. They've been around since the 50s. And so that I found very interesting, and the newer quantum sensors are not outperforming those sensors. And the other thing to take away from this chart is that if you look at the y-axis, they're not really even exceeding the 10,000 meter range. So that's quite small when you think about the vastness of the ocean, if you were wanting something like complete ocean surveillance. So then when you think about taking these technologies and converting them to operable capabilities, I would say there's two main ways in which you would want to undermine a second strike capability. One is this term called transparent oceans. It's kind of this idea that you'd know where anything is in the ocean at all. It's like the gold standard, but pretty far, I mean, extremely far out. A lot of people doubt that you would ever have transparent ocean scenario. And so just by considering the vastness of the ocean, you would need at least hundreds of thousands, if not million sensors based on the sensitivities right now. And a lot of those sensitivities I would give very generous estimates to, where I looked at sensitivities that have been achieved in lab settings. So I don't expect those to be surpassed in the real world environment, at least in the next 10 to 15 years. And then you might say, okay, well, I don't need to know where everything is in the ocean. I just need to be able to track the submarines and know where they are. In that case, maybe you could say, what if I have some information about the submarines, or I follow them and I'm able to deploy persistent tracking capabilities? But then you would still need networks of AUVs, UUVs, or nuclear submarines, and that assumes a much higher level of risk, because then your adversary becomes more aware that you are tracking their submarine, which creates strategic stability issues. And I think it still becomes an issue, because in those areas, in those cases where you don't have transparent ocean and you just have persistent tracking, if the sub is able to lose you, then you lose your first strike capability. So to me, that just injects more uncertainty. And then I also look at countermeasures that could cheaply and effectively diminish the improvements from quantum sensors. So specifically improvement in stealth capability, or the ability to suppress the signal from the subs, is something that we've been doing for a long time, and we can expect that to get better, at least a little bit. I mean, we're pretty much, I'm going off of open source estimates, but we're exceeding certainly 95%, potentially 99%, but you could still suppress it even more. And as this shows, that would then decrease your detection range. But you could also cheaply spoof the sensors with decoys, or jam them with pulse emitters, or even interfere with the sensor network itself by, you could easily imagine programming a UAV to take out some of the sensor buoys, and then that creates an upkeep issue that makes it more difficult to upkeep. So what I'm doing this year is also looking at ocean characteristics, which I don't even account for here. So this is assuming like the ocean characteristics remain the same, and that's clearly not the case. Shallower waters and deeper waters have very different issues that you'd have to overcome. So I will leave that at that. But then when I was looking at the missile navigation case study, I wanted to see if it was possible that quantum sensors could improve missile navigation, or increase the accuracy of missile navigation. And as I mentioned with the second strike introduction, the impact of this would be that it could allow for taking out those deeply buried or more protected silos. And so the term that people use to estimate missile accuracy is kind of this funky term called circular error probable. And it just designates this radius at which 50% of missiles are likely to fall within the radius. And so you want that circular error probable to be small if you want a higher accuracy missile. And so, we've been successfully decreasing the circular error probable and increasing the missile accuracy over time since we've had missiles. Now the US and Russia are around the 100-meter range. I mean, there are different estimates, so I don't, I'd say roughly 100 seems to be where a lot of the estimates are. And China's likely to be approaching that as well. And the important thing here is that if you think about the blast radius for a nuclear weapon, 100 meters actually seems kind of small. And that, if you can get within 100 meters, you can probably take out a silo with a very high yield nuclear weapon. But as people are pushing for nuclear or counterforce capabilities that better align with the law of armed conflict, you would want lower yield nuclear warheads, or potentially even conventional counterforce capabilities that could then destroy silos and potentially allow for taking out silos with lower casualty and fallout. And that would be very impactful, and it would be, very hard to push back against counterforce capabilities. So that is why a decreased circular error probable would be pretty important to consider. There is like very little publicly available information, not surprisingly, or not unsurprisingly, about missile accuracy. So what I did is I took the determinants for the circular error probable, which are outlined by Bunn and Sippes. And I tried to walk through and figure out how quantum sensing would increase the accuracy in each of these or decrease the error in each of these contributions. And, identify a couple ways. Obviously, better sensors impacts the error coming directly from the sensors, but it could also impact some of the knowledge of other factors as well. But then I did the same thing that I did for the summaries, which is look at the sensitivities for current sensors. And once again, quantum sensors are not exceeding existing sensors. So ring laser gyros and MEMS, which are at the bottom, have higher or better sensitivities. Remember, the smaller number is actually good in this case. The issue is that they just are bulkier or have more drift over time. So the promise for quantum is that you could get decreased size, you could dead reckon with less drift, which impacts that, it would lower that error bar. And actually, potentially the most important would be map matching navigation or recalibration, which could allow for recalibrating in the reentry phase. And the significant part there is if you can recalibrate in the reentry phase, you can actually scrub a lot of the errors that have accumulated throughout the flight. And so there has been an experiment run by I think it was the US Navy in the 90s with a maneuverable reentry, but it was using GPS signal, which you can't assume that you would have in a crisis scenario. And it was able to get within 10 meters when it did navigation in the reentry phase. So that just shows, if you could get reentry navigation with quantum sensors, you could imagine that shrinking. But I say, even if you think you can get navigation within the reentry, there's still some operability issues that you can't count out, which is the remaining uncertainty in kill dynamics and the probability that you will destroy the silo just by striking it. We don't know as much about the kill dynamics for low yield and especially conventional warheads as we do about larger yield warheads and the pressure distribution. And then, you could imagine countries using decoy silos, which are empty, but would require more warheads to target. And then you could also imagine this being offset with point missile defense, or even something like grates or pebble beds, which could redistribute the impact from specifically conventional, would actually help to increase the uncertainty that the missile would be destroyed. So the main findings from the technical analysis is, well, actually, the trajectory of quantum sensing itself, like the other case studies that I suggested, is longer than you would assume by the title of an emerging technology. And so this seems kind of simple, but I actually think it reveals a pretty important finding, which is that this technological surprise or this risk that everybody's afraid of is probably unlikely. Significant and rapid disruption rarely happens. It might happen if you're just ignoring the background of technological research and development. But if you're tracking what's happening in the technical fields, technologies are rarely going to just emerge that outpace things you've been working on for decades. More progress is likely with quantum sensing, but as I've showed, remaining obstacles are expected, and you can expect significant experimental and operational hurdles to prevent you from ever saturating the limits that people have proposed. And then methodologically, I think what I learned through the technical analysis was that it's just hard to analyze across sets of emerging technology because you're comparing technologies, even within the case of quantum sensors, that each operate very differently. And so I can show the sensitivities, but I'm not capturing all of the operational differences between the sensors. I do when I write this out, but when I present, it's very hard to show that each one is different. So it's very hard to compare. And so you're always going to have some element of uncertainty when you're analyzing these new technologies, which is where the strategic interpretation comes into play. So, I would say from the case studies and just intuition, I think it's become apparent that assessment of technological feasibility alone rarely produces consensus on the effect and the opportunity for new technologies. And as I've showed, there's inherent unresolvable uncertainties. And so when you have those uncertainties, how do policymakers make decisions? And that is where these strategic disagreements or even social pressures come into play. And so when I did this analysis, I looked specifically at disagreement that arose from the assured destruction and damage limitation camps and deterrence. But you could imagine similar differences arising due to different theories about how security works or deterrence or other deterrence strategy aspects. In this case, I'm considering assured destruction, where you only view that you need a minimum means of retaliation for a deterrent to work, whereas damage limitation proposes that you would want to continually improve your offensive and defensive capabilities to achieve better deterrence or even compellence. And ultimately, what I show, and I'll show in the next chart, is if you have different perceptions for how deterrence works, it informs your view of not only the effect for technological improvement, but how you treat uncertainty regarding the new technologies and risks and benefits for pursuing the technologies that then shape your view on whether we should engage in arms control, force structure, or other technology acquisition policies. Okay, so if I line up assured destruction, damage limitation, and I think, okay, what would be the disruptive capability threshold needed to undermine second strike? Assured destruction has a very high threshold. And so for them, they would say this is only impactful if the improvement allows for complete surveillance of submarines or complete targeting certainty that you could take out essentially you could take out the full second strike of an adversary. Whereas damage limitation actually has a lower disruptive capability threshold, where any incremental improvement could increase your offensive capabilities and reduce your adversary's retaliatory force. And then they both treat uncertainty differently, like I alluded to. From the assured destruction camp, any remaining uncertainty actually bolsters your view that it is unlikely that new technologies would fundamentally undermine second strike capabilities, whereas the damage limitation camp would view uncertainty and say, we need to continue to pursue these technologies so that we can prevent the possibility for an adversary to manipulate the technology, or any uncertainty that they might get the technology and get an asymmetric advantage. And then the perceptions and risks of pursuing the technologies are also viewed differently. So if you have an assured destruction view, you would say, okay, well, improvements could increase strategic stability risk if they disrupt mutual vulnerability, or actually impact people's perception of mutual vulnerability. So even if we don't believe that mutual vulnerability will be disrupted, but policymakers do, that would increase strategic stability risk and could incentivize arms racing. Whereas damage limitation would say that there's lower risk and potential benefits from acquisition, and actually the higher risk is from technological surprise by your adversary. So this is just to show how you would take in the same information completely differently depending on your underlying deterrence views. And then beyond that are the effects of social factors. And so I don't have a ton of time to go into this, but I just want to make the argument that, I think accounting for non-strategic and non-technical factors is equally important. So social dynamics further complicate policy decisions because they can lead to inflated expectations around new technologies. There's a lot of new dynamics for science communication that are showing that science communication is being hyped. It can introduce institutional biases or parochial interests that impact decision-making processes, and the actual organizational structure can impact how information flows across actors. So not necessarily that they are making decisions because they are rejecting information, but they just don't have access to the information. My reason for thinking that accounting for the social factors is important is that if you think about it from the social construction of technology lens, which is a more constructivist approach to how technology develops, and it says that technology arises because of social influences, you can have more proactive policies. So if you only apply technological determinist lens, which is this idea that technology emerges and therefore we have to respond to it, then you're really constraining your policy options to responding to the technology as it emerges. And I know there's a lot of pressure whenever I talk about this with policymakers and to push for the technological determinist argument and say, well, we have to respond to this. You could see it in the Oppenheimer movie when people say, well, if we did not do that, then the Germans would have. And it just is a pretty common rhetoric. And I'm not going to say across the board that technological determinist views are invalid, but I would say that when I mapped out all of the quantum sensing research groups in the US, 96% of them are funded by the government. And so to me, that shows pretty powerfully that, you know, even if you think a technology evolves at some rate independent of social decisions, there is still a lot of influence from social factors that shape how a technology develops. And so that's where you have more room for proactive policy development. So I'm not going to get into the actor network and social dynamics, but it led me to kind of isolating the different areas of policy recommendations. But I looked at factors that are influencing technologists and epistemic communities, so the technology producers. And then I looked at capability seeker communities and what sort of social factors are incentivizing them to continually seek out certain capabilities that simultaneously reduce some vulnerabilities, but introduce new vulnerabilities. So it's this reinvention of vulnerability cycle that kind of pushed my research for the next phase. And then just larger institutional macro social trends that are just changing technology communication or technology funding that we would want to consider if we're thinking about broader policy options. So the conclusion that I have is that, you know, from my analysis, quantum sensing actually follows the cyclical trends of reinvention of vulnerability and accuracy and deterrence that we've seen in other technologies. It's not really new, and you know, a lot of the actors are the same. The strategic stability implications are that quantum sensing will have more evolutionary rather than revolutionary effects on capabilities, but that this will be perceived differently depending on different deterrence predilections. And policies in favor of technological hedging and hedging against technological surprise, which are promoted by damage limitation proponents, actually underemphasize arms racing risks and inflate potential benefits. And then the broader literature, I think the implications for this is when we see these articles talking about how we could use emerging technologies to kind of push back against stagnancy in the nuclear field. I think this shows that something deeper is that we really need to get at the heart of these disagreements between assured destruction and damage limitation arguments. And we can't expect these newer issues to try and, you know, break that stagnancy. Okay, I'm at time, but I do have, I broke it up into recommendations for mitigating strategic stability disruptions, largely around, you know, I recognize that there's disagreements, but there are some arms control options where you could increase the availability of information to all actors. And then I broke out into policy recommendations for mediating quantum sensing perceptions, which largely revolve around increasing the amount of oversight in the government for technological decisions, which actually has significantly decreased since the Cold War. You know, the congressional OTA is no longer around. And so we really need to focus on getting more technical or technologically literate people into the government to transmit this information and building connections between the government and the technology producers so that there's better information flow. Okay. And I don't have time to go over the limitations, but so there.
All right. Thanks very much, Lindsay, for the very provocative presentation. To those who are in the video audience, if you have questions, please add them to the question category here. Just looking, making sure. Yeah, questions. And for those in the room, we'll follow the tradition. 1 finger to get on the queue, 2 to jump the queue to make a comment on the subject under discussion. And we'll start with opening the floor to our fellows for the first questions. And please identify yourself as.
Hi, Lindsay. Thank you so much for your presentation. My name is Neely Habe. I'm a Indo-PACOM visiting scholar this quarter. So what really sparked my interest was this concept of reinvention of vulnerability. And I was just curious if you had any ideas on how to limit these capability seeking communities, and maybe seeking out these new technological capabilities isn't always the right answer. I'm thinking from a policy perspective.
Yeah, I mean, so that's kind of where I'm trying to go in the next round of research, and that I'm gonna try to expand beyond just quantum sensing. And there's this larger, the name reinventing vulnerabilities kind of draws from the invention of accuracy, which is a socio-technical analysis of how accuracy has continually evolved in the missile community, and in turn has led to or counter capabilities that have pushed back against the improved accuracy, but also have then informed how we view vulnerability of capabilities. So it's a larger socio-technical evaluation. So I'm trying to show you can do all this analysis, but if your target at the end of the day, where you're trying to evaluate the strategic effect, is also a moving target, which is vulnerability, like this term, and if that's changing over time, then we hit a real issue with being able to evaluate things. And I think there are a lot of social pressures where, interestingly, in the capability seeker community, people who are pushing for quantum sensing because it could afford better offensive capabilities are not thinking about then how it impacts their defense. And so there's a big offense defense reaction cycle. There's also a lot of parochial interest too, because there's literally the same technologists that are making quantum sensors to improve missile accuracy or submarine detection are also contributing to efforts to improve stealth capabilities or counter capabilities. So it's like this huge cycle that then kind of, I think at the end of the day, it pushes us towards arms racing if we accept this cycle of continually changing metrics for evaluation, which is why I care about pushing back against it. But yeah, glad.
You have a two finger at the back. Yeah.
Hi, Arzan Tarapur. I work on South Asia. I'm glad you just raised this issue of the sort of measure countermeasure cycle. And this is a technical question. For quantum sensing, are countermeasures technically feasible, possible? Because when as a non-technical person, when I hear about quantum computing, one of the key takeaways of that is that there is no that it can break any code, right? That there's no crypto defense against it. I don't know if that's also just hype or not.
Well, for the quantum decryption, they are working on standards to NIST is working on standards to employ post-quantum encryption. But that is a very unique case where I think that is one of the fundamental issues with quantum computing. But that is different from in the is this not from in employing these operationally. And that's something I push back on people who are saying that these systems are going to become vulnerable, because actually in the literature, people like Lieber and Press, who I've talked with about this, so we've had this debate, so they know I disagree with them. But they say countermeasures are not important or not as important to consider, because the countermeasure will always favor the country with a technological lead, because they will have a better capability to deploy countermeasures at the same time as they are also deploying the measures. But I don't agree with that, because I think if you even think about these jamming, spoofing, and interference, those are actually cheaper and much easier to do than actually developing a quantum sensor. So in the case of quantum sensors, and maybe it is case dependent, I would say that the countermeasures are easier to produce and quicker to produce. But I think people are always thinking there's going to be some gold standard where, like, maybe we launch one satellite that could see the whole ocean, and then
you only have to look at how hard it was to find the Scuds in Iraq, right?
Yeah, well, that's what the psychics are for.
Is this another two finger?
No, I have a new.
Okay, then hang on. Max is next.
Hi, I'm Max with CSEC and Sari. Thanks, Lindsay, for the talk. It was great. I like the question of how perception impacts policymaking and vision with these technologies. I was wondering, to question, in your studies, if you come across cases where you think, hey, this is actually how we could have done it better, for example, with a more technological review. And as a follow-up, how do you think modern social network, accelerated misinformation, and democracy impacts these kind of solutions that we might have? Thank you.
Sorry, so for the first question, what was the?
Did you find, because you said, okay, there definitely is an impact of the perception on the policymaking, and just a set of solutions that you maybe found in your studies on the historical cases, what might work, what might not have worked?
Yeah, I mean, so that's why I think having more technological knowledge in the government is helpful, or at least more engagement between policymakers and the technology producers. So it used to be more mechanisms for oversight that could help address some of the perceptions. You know, I don't get into whether or not the perceptions are driven by personal interests, or I try to keep it, you know, assuming the best intention. Sometimes people are taking advantage of perceptions, producing perceptions like, and you were saying social networks, I mean, to get more viewership, or like those articles were saying things that are like fundamentally crazy, but, and any small amount of research could show that, but they get viewership. And so that's in the media, but in the government, you know, sometimes whether or not it's intentional, pushing for technology with a false perception can help you get more funding in your department, or it can help you increase your ability to engage with higher level policymakers. So there's a lot of reasons why there are sources of inflation in the perception. Yeah.
Cameron? Well, we'll do Cameron next, and then we'll get back to
Cameron Tracy, CSAC research scholar. Thanks for the great talk. I had two questions. One, a quick technical one. Squids in the lab need to be cooled, of course, the superconductor part, so that's liquid nitrogen. In this idea of millions of these stationed across the ocean, has anyone like seriously proposed how you're doing that? And then the second question, more substantively, an undercurrent to a lot of the arguments you're making is that the category of emerging technologies is not doing the analytical work that many in the security studies community seem to feel that it does. So when it comes to categorization at a lower level, you also ran into this problem when you had your grid of where to put missile defense for similar reasons, because this is an umbrella category where SDI would probably fall in a different box than Patriot-style terminal defenses. And you get the same for hypersonics with scramjet cruise missiles and glide vehicles. And then, of course, for quantum sensing, you made the point that grouping these as quantum sensing is kind of artificial in the first place. So do you have a sense of where that categorization, which in some of these cases is quite recently developed, is coming from? What work is it doing if it's not analytical work?
Yep. I mean, I have thoughts. Okay, so for the first one, I mean, the squids, that there are thoughts about deploying sensor networks. Nobody has actually talked about the issue of actually doing it, which is why I don't even have to get into the fact that I think it would be really hard. I'm trying to give it the best case scenario. You know, maybe we get chips to scale cryogenics, but it's still a lot to upkeep. But I totally agree. Like with squids, that's the issue with squids, is they're really only useful for port detection because you need a pretty huge flying device. Mostly they're used with planes. Sometimes now we have UAVs. And yeah, there's a huge energy draw. So I didn't even get into the energy analysis, but I also look at how much energy a lot of these products use, and the energy pull is enormous. So even with some of the quantum sensors, which don't need cryogenics, then you need a lot more energy pull because they're often optically based, which is lasers, and then pulls a lot of energy. Oh my God, on the categorization of emerging technology, I have a lot of thoughts about this. You know, being a younger person in the nuclear field, I don't think people are trying to push emerging technologies to have a negative impact, but I think often younger people are pushed towards emerging technologies and away from actually talking about these fundamental issues in the deterrence community because they seem like topics that other people have a handle on. So there's actually like a huge social aspect of that, of like, okay, well, if I'm in the nuclear community, I have a much more likely chance of getting funded if I'm saying that I'm working on emerging technologies than if I'm working on damage limitation and assured destruction. So I think we kind of bubble it up nicely in that. I also think, like I said, I mean, I think that there's a lot of people who genuinely believe it could help resolve disagreements. And so I think, you know, I came at it from that approach too before I did this research. And so I think that, you know, that is a good intention. And then sometimes, you know, especially in cases where technologies are huge, like missile defense or even hypersonics, I think we use these terms. There's a term in the STS community, I have it on here, but I'm not, boundary object. So we like bundle them up to try and make it a manageable task. And then in doing so, we lose some of the resolution about what these technologies actually, what we mean when we say them, and our ability to kind of understand. So. Yeah.
Is that a two-finger, Paul?
Yes. Yes. Yeah. It's very deterministic when you read these. And that's why, like, I'm just trying to focus on the people aspect too, because everybody's saying these will emerge. And I think, you know, in some cases they could, and they're likely to, but we can also shape how they emerge. And that's why I think you have more options for proactive policies. If you top that.
Right, please. Turn the microphone on, please.
My new question turned into be a follow-up question to Paul's comment. I'm Callie, I'm a biosecurity fellow. So I have a question about what as it relates to bio. So as you were doing your technical analysis, it seemed like a lot of stuff was not easily accessible because it was not things that were like published in places that all of us could read. And I think that that's really different from a lot of the work that I do in bio, where it's actually extremely accessible, as Colin mentioned in the last seminar. And so I'm curious how, as different types of emerging technologies that, for example, have genesis in different spaces, right? Like community spaces, for example, or outside of the government or outside of academia, even, how that influences our thoughts about vulnerability in emerging technologies and weapons.
So the availability of information. I mean, I think it's a huge role. I'd say also an interesting part about that is probably one of the biggest risks of my research, which I've had to think about very seriously, is the fact that although people think the US research community publishes and is like very open, if 96% of quantum research groups, quantum sensing research groups are being funded by the government, then a good majority of those are probably not publishing some of their sensitivity levels, which is a huge risk for me, because if I'm going off of publicly available sensitivity levels, then there's always a chance I could be underestimating. I try to go with the highest estimates to give the best case scenario for the technologists and the capability seekers. I'd say more the issue is just dealing with people. There's also an STS, like Chris Lawrence, who used to be here, said that there's like a social scene set up when some people have access to classified information, some do not. And so that's probably the biggest issue. I don't know specifically for certain fields. And if it's more or less in bio, definitely as you move more towards application and capabilities, that's where it becomes very gray. And that's why it's really hard to map. I don't know if that's harder or easier though in other fields, but we looked at quantum. Yeah.
All right, we're just about to run out of time, and this is not a question from the ether, but a request by Bob Vince. Could you put your last slide up? You went through it quickly, and we'll leave that up. And then very quickly from fellow Rhiannon Nielsen, you showed that 96% of the funding for in the quantum field, I think, was from the government, and I'm shortening her question. To what extent then, and how does this affect decisions by institutions about their research programs?
Yes, I mean okay. first of all, it's quantum sensing. I only looked at quantum sensing. I have mapped out funding for all of quantum, and actually it really varies. So for quantum computing, there's a lot more private interest. So that's the only reason I have that distinction. I mean, the whole reason I started adding the parochial interest thing is because when I started this research, well, I can't see who's on, but hopefully this person's not on. I interviewed someone who is a technologist who is responsible for getting funding from the government. And he said, I would never tell a funder this, but this is not going to work. And so that kind of started me down this whole path where I was like, this is why I need to look at that, because that is a big source of miscommunication. And so the fact that funding hinges on these certain capability applications definitely impacts what people are allowed to apply for, how they apply for it, and also how they communicate it. So that is a big push in science communication of why people have to overinflate the effects of their research. And, you know, I think it's not to be nefarious. A lot of them are doing it to get funding for grad students, but I don't think they're thinking about how it's impacting how policymakers are perceiving the state of research.
All right, on that note, let's thank Lindsay again.